Okay, so hello everyone, welcome to our channel Non-IITian, and if you enjoy the content, don't forget to like, share and subscribe. So in this particular video, we are going to talk about a very interesting problem which has come in CSIR NET. I forgot to mention it. Probably it was June 2020. And the problem is regarding an entire function. Let us first understand the question. So the question says that for some complex number z, let this denote the real part of that complex number. Let f be an entire function such that mod of fz is less than or equal to mod z times mod of the real part of z on C, that is on the entire complex plane. What can we conclude about the function fz? Okay, so we need to formalize the structure of the entire function f. Okay, and so there were four options. I have intentionally removed those four options so that in some sense we do not get an idea immediately what we need to prove, but nevertheless we will prove this following fact. And this sort of a statement should be sort of familiar to people who deal with complex analysis problems, that we will show that there is only one possible function. To emphasize, there is only one possible function that satisfies this condition, and what is that possible function is what we are going to find. So what are the key concepts we require? The first thing is the definition of an entire function, which I am repeating formally. So an entire function is a function that is complex differentiable or holomorphic at every point in the complex plane. And the next thing, which is actually the important thing which we require, is what I have named as concept 2, is the identity theorem. And it's an extremely powerful theorem in complex analysis, which says the following. It states that if the set of zeros of a non-zero entire function has a limit point in C, then the function must be identically zero. In simpler terms, the zeros of a non-zero entire function must be isolated. That is, the set of all zeros of an entire function, of a non-zero entire function, cannot possess a limit point. Otherwise, it will be identically zero. Okay. Now let us move towards what we want to formalize. So what should be our strategy here? What we'll do is the following. We'll try and investigate the behavior of the function f of z on the imaginary axis, and then we'll use the identity theorem to deduce its form. Okay, and why are we actually trying to do that? Because we'll see that, the idea behind is the following. Okay, let me just formalize it a bit. See, let me go to the pen. So on the imaginary axis, the modulus of the real part of z would actually come out to be 0, and that's exactly what we will be trying to use. Okay, and then we'll use the identity theorem. And why are we going for the imaginary axis? So the first reason is this, and the second reason is that the complete imaginary axis is not a collection of isolated points. It admits limit points, obviously, right? If you have very simple topological knowledge, you'll obviously deduce the fact that the imaginary axis will obviously yield limit points. Okay, now let us do our job. So we are given the function f of z, which is less than or equals to mod z times the real part of z for every z in the complex numbers. So we traverse through the imaginary axis. Okay, so now if I traverse through the imaginary axis, then what should z look like? So z should look like iy, where y is a real number, right? And as I said, for any such point, the real part is 0. Therefore, what do I conclude? We conclude that the modulus, so the modulus of f of iy, which should be less than equals to modulus of iy times the real part of the modulus of the real part of iy, this should be 0. But the modulus of something is less than or equal to 0. What does that mean? That means that the the modulus of f of iy must be exactly equal to 0. But that means that the f of iy is exactly equal to 0 for every real number y, right? What does that mean? That means that f is 0 on the imaginary axis, right? Therefore, the 0 set of f, it consists of the entire imaginary axis, and the entire imaginary axis admits limit points, right? So therefore, let S be the set of zeros of f set. So S is nothing but the collection of all those complex numbers such that f of z is 0, and this collection has a limit point. Any point on this line is a limit point for sure, right? The set of zeros of fz is therefore not isolated, and hence what can we conclude? So therefore, by the identity theorem, since f is entire, f must be identically 0, and that's exactly what we require to prove. So f is just the identically 0 function. And probably the options were, so option 1 was that f of 0 is 0, which will be true. Option 2 was f prime at 0 is 0, which should also be true. Option 3 was exactly this statement, that the only function which satisfies this condition is the function identically 0. And option 4 was that there is some non-zero entire function which satisfies this condition, so that should be a false statement. So this was a 4.75 marks question. Okay, so the final conclusion that the only entire function that satisfies this given condition is f of z identically 0. So thank you for watching. Please do like, share and subscribe to Non-IITian. Thank you.